Hey guys, it's Alex from EDD Academy, and today we're going to be looking at easy ways to memorize trig and inverse trig derivatives. We're going to start with the basic trig derivatives rather than the inverse trig derivatives. But before I get into these, I want to say that if you're looking for a video that talks about the derivations of each of these functions, you can click off this video and go watch EDD Academy's deriving other trig functions video in Unit 3. So to efficiently memorize all of these basic trig derivatives, I want to lay out some rules that will apply for pretty much every single one and simplify them greatly. So first of all, any function starting with c is negative. That means cosine x, cotangent x, and cosecant x. Cosecant x will all be negative. Number 2, anything relating to tangent has a squared term and involves the opposite function. So anything relating to tangent, that's just tangent x and cotangent x. So each of these will have a squared term and involve the opposite function, where the opposite function for tangent is secant and the opposite function for cotangent is cosecant. Similarly, anything related to secant has two parts and involves the opposite function. So cosecant x and secant x all have two parts in their derivatives and involve the opposite functions. Like I said, the opposite function of secant is tangent and the opposite function of cosecant is cotangent. Okay, now we can actually get into our derivatives. As you can see here, I plotted the original trig functions on the left versus their derivatives on the right. I've also recopied the rules we learned last slide to have as a reference because they're quite useful. So you might think you know all these derivatives pretty well, but even to this day, I have trouble memorizing cotangent, secant, and cosecant x just because they're a little bit trickier functions and we don't use them all the time. But these tricks are literally what helped me memorize them, and I don't think I will ever forget them. So let's start. As a kind of universal rule that I didn't mention as one of these special tricks, each function will involve its opposite function. It will flip in some way. So for sine x, its flip function is cosine x. And because it doesn't fit any of these special rules, we just leave it at that. Cosine x, so we just flip that function as well. We get sine x, but wait, it starts with a c, so what do? Add a negative. What about tangent x? Tangent x, it doesn't start with a c, but it does relate to this second rule here. So if it's related to tangent x, it has a squared term and involves the opposite function. And we saw that the opposite function of tangent is secant, and it has a squared term, so it's just secant squared x. Cotangent is very, very similar. It has a squared term, involves the opposite function, so it's cosecant squared x, but it has a c, so what do? Slap a negative on the front. Moving on. Secant x. What about secant x? It doesn't fit either of these two rules, but it fits the last rule. So it has two parts and involves the opposite function. So anything related to secant has two parts instead of a squared term. So it involves the opposite function, so tangent x, and it has two parts, but if it involved the opposite function again, it would have a squared term, tangent squared x, right? So it's tangent squared x times the original function, tangent x secant x, or most popularly written as secant x tangent x. The same goes for cosecant x. Has two parts, involves the opposite function, does not include a squared term, so it's cosecant x cotangent x, but it also fits this first rule here, so it's negative. Well, that's it. those are our basic trig derivatives. It's pretty easy. Now you might be slightly intimidated by the inverse trig derivatives because we haven't been exposed to them yet. But trust me, with the rules you're going to learn very shortly, they're going to be a piece of cake and just as easy to memorize as those regular trig derivatives. And what makes them so easy to memorize is, again, a set of 3 basic rules that you will always follow. So rule 1 is the exact same rule 1 as for regular trig derivatives. Every function starting with c is negative. But instead of cosine, cotangent, and cosecant x, it's, well, the inverses of those functions. Rule 2, this is a new one, use your Pythagorean trig identities. You always need to know your trig coming into calculus, and this is a prime example of it. So the most popular example probably being sine squared x plus cosine squared x equals 1. We're going to use these. And then the last one, another new one, cofunctions are related. Directly related, most of the time, or in fact all of the time. So sine and cosine, they are going to almost mirror each other. Tangent and cotangent, same thing. Secant and cosecant, they're going to be very, very similar to each other. Okay, now let's get into it. For the inverse trig derivatives, I wanted to structure this page a little bit differently, with the rules featured more prominently at the top and each of the inverse trig derivatives at the bottom. But instead of doing them all on one page, I'm going to split the inverse trig derivatives into cofunction pairs. So here we have sine inverse and cosine inverse, and then on each slide we will have the rest of them. So for sine inverse, let's see. It doesn't have anything to do with c, it doesn't start with c, so we know it's not negative at least. And like I said, we have to do this a little bit more intuitively, so let's just write it out. So what is sine inverse of x? So sine inverse of x equals y. That's our function, right? We learned in the inverse derivative video at the very beginning when we reviewed some algebra stuff that we can rewrite this as sine of y equals x. And well, we can just take the derivative of this using implicit differentiation. So d dx of sine y equals d dx of x, right? That's just simple implicit differentiation. And if we actually take the derivatives of these, the d dx of sine y is cosine y times dy dx, because the derivative is with respect to x, not y. And then d dx of x, because the derivative is taken with respect to x and we're dealing with a function of x, we just take the derivative of it with no extra term, so the derivative of x is just 1. And what do? We want to solve for this term here, dy dx, right? So we can just divide both sides by cosine y and get that dy dx equals 1 over cosine y. But then we have to use this second identity, or the second rule, that says use the Pythagorean identities. The one we're going to use here is the fact that sine squared x, or rather sine squared y plus cosine squared y equals 1. If we apply that to this example, we have dy dx equals 1 over the square root of 1 minus x squared. And that's the derivative of sine inverse. So 1 over square root of 1 minus x squared. And we can invoke this third rule, cofunctions are related, very similarly. And we can also pair that with the fact that any function starting with c, which cosine does, is negative. So it's literally just negative 1 over square root of 1 minus x squared. Luckily for us, tangent inverse and cotangent inverse are very similar to sine inverse and cosine inverse. Once again, we take the function that we're trying to look at, tan inverse of x, and set it equal to y because it's our function. And using inverse rules, we have tan y equals x. I'm going to box that here because we're going to be using it later. And like we did last time, just take the derivatives of both sides. So d dx of tangent y equals d dx of x. We should be pretty familiar with implicit differentiation right now, so I'm going to kind of rush through this. But tangent y, that's just secant squared y. We learned that a couple videos ago and reiterated it a couple minutes ago. And then because this derivative is with respect to x and we have a function of y, we need that dy dx term at the end. And then d dx of x, that's just 1. And once again, we solve for dy dx. So divide both sides by secant squared y. So 1 over secant squared y. And once again, we have to invoke one of our Pythagorean identities. But instead of invoking the one that says sine squared x plus cosine squared x equals 1, we're going to use the one that says secant squared y equals tangent squared y plus 1. But remember, I said to keep this in mind and box it? Look at this. We know tangent y squared in terms of x. If we know tangent y equals x, then tangent y squared, well, that's just x squared. So secant squared y equals x squared plus 1. And we can rewrite our derivative in a final form of dy dx equals 1 over 1 plus x squared. So we just write that in here, 1 over 1 plus x squared. Cofunctions are related, and it starts with a c. Cotangent inverse is as simple as negative 1 over 1 plus x squared. Last but not least, we have secant inverse and cosecant inverse of x. And before I start, I want to note that I've included use geometry as a part of our second special rule, because not all the time does the Pythagorean identity work. There's only a limited number of them, so it's not going to work in every single case that we have. But yeah, just keep that in mind, and we're going to use geometry or right triangles later. So until that point in the problem, we use the exact same tactics as we did before. So secant inverse secant of x equals y. That means secant y equals x. Pretty standard. Take the derivatives of both sides. That's pretty much the only calculus we know. So d dx of secant y equals d dx of x. Implicit differentiation. We know the derivative of secant y, well, if you've been watching this video, you know the derivative of secant y is secant y tangent y. And because we're differentiating with respect to x, and secant y is a function of y, we slap on that dy dx term. And that's just equal to the derivative of x, which is just 1. Let me bring this here. We want to solve for this dy dx term. We just divide both sides by secant y tangent y. Get rid of it on this side, and then we have dy dx equals 1 over secant y tangent y. And like I said, we don't actually have an identity for this. So we whip out some right triangles and do some good old-fashioned geometry. So here is my horrendous rendition of a right triangle, but it'll do. So it may seem like we have no information about this right triangle because we don't see any sine, cosine, or tangent here, right? But you have to learn in calculus that you can actually deal with triangles in trigonometry without SOHCAHTOA. So, we can actually see that we know something about this triangle. We know secant y equals x. And you might say, where does secant y come into place? Well, what is secant y? Secant y can also be written as 1 over cosine y. And what does 1 over cosine y equal? It equals x. So what does that mean cosine y equals? Well, you just flip it. Cosine y equals 1 over x. And if we set this as our angle y, that's pretty easy with SOHCAHTOA. So, the adjacent over hypotenuse is 1 over x. So that means this side is 1, and the hypotenuse is x. And using our Pythagorean theorem, basically another Pythagorean identity, we find that this side is x squared minus 1. And now that we have all sides of the triangle, we can actually find tangent y, right? Opposite over adjacent. So tangent y equals opposite, square root of x squared minus 1 over 1, which is just the square root of x squared minus y. So now we have everything in this field. Secant y, that's just x, and tangent y is square root of x squared minus 1. So dy dx equals 1 over, don't forget that, x squared minus 1 times x. But mind you, can x be negative in this case if it's the length of a triangle? No, it can't be. So we put some absolute value bars over it. And that is our derivative. Look how beautiful math is. We input this into the table. 1 over the square root of x squared minus 1 times the absolute value of x. A little bit complicated there. And then slap a negative on the front for cosecant inverse. Negative 1 over x squared minus 1 times absolute value of x. And that's basically the end of the video. Thanks for watching.